All right, so let's take a moment to actually look at what can happen. Because if you recall back to the last example we did before this one that you're seeing on the screen, you remember that we actually, I'll just pull up the example, the system of equations that we solved is right here. Right? This is a system of three equations and three variables. And through some work, we were able to determine that the solution to that system is given down here. So there's one solution, right? There's three values, 1, 2, and 3, but that's because there's three variables, x, y, and z. There is one solution, and in the sense that a solution is an assignment of values to the collection of variables that makes all the equations true. So there's only one solution. X, y, and z have to be 1, 2, and 3, respectively. And then in the example we did after that, most recently, we had this system of two equations and two variables right here. And it turned out that because of this contradictory row, there was no solutions at all. There was not a single way you could assign values to the variables that make all the equations true simultaneously. So that system of equations had no solution. So what other possibilities are there? That's the next question we're going to answer. I mean, at least it seems reasonable to say that, well, could a system of equations have two solutions? Could it have three solutions? What about, could it possibly have four solutions, but not a fifth solution? It probably doesn't really seem unreasonable that that's possible, but it actually turns out the answer is no. You're either going to have one of three cases happening. There's either going to be one solution, there will be no solutions, such as this case here where there was no solutions, or you could possibly have infinitely many solutions, but there's no fourth option. So you're either, as soon as you have more than one solution, you already are going to have infinitely many solutions. That's my claim to you, and I'm going to try to convince you of that by drawing a few pictures, but in the specific case of having a system of two equations and two variables. So let's start by writing down the most general 2 by 2 system we possibly can. Remember, 2 by 2 means two equations and two variables. So consider the linear system given by the following. So we've got ax plus by is equal to c. That's the most general linear equation in two variables that you could write down, but I want to write down two of them. Right, so I'm not going to just stop here. I'm actually going to give indices here. I'm going to put a 1 as an index on the coefficients a and b, and also a 1 on the constant term c. So my coefficients are a1 and b1, and my constant term is c1. And for the second equation, I'll copy the same approach, but I'll use a 2 as the subscripts for each one. So I've got a2x plus b2y is equal to c2. So that's the most general linear system of two equations and two variables that you could write down. So what can happen? Well, it's important to first make the observation that these equations really represent lines in R2. So these represent lines in R2. Okay, so what can happen? If you had two lines in R2, what are the possibilities? So one case is you could have this situation. So case one, I'm going to draw an x and a y-axis. You could have this situation happening. I'll just highlight the origin. Okay, you could have one of the lines going across like that, and then maybe another line goes like that. That's one thing that can happen. Now, what happened here? In this case, the lines intersect at this one point. And it turns out, if you think back to when you first talked about systems of two equations and two variables, this is actually might remind you about the graphical approach to solving systems of equations, which I didn't discuss in this section, but you might remember discussing that. And in that case, you'll remember that the point where these two lines intersect, that's actually the solution to this linear system. So in this case, you have one solution. So that's a possibility, right? That's not the only possibility. Another possibility, which we'll sketch below now, what's another thing? Well, let's draw the x and y axis again. Got the origin, and then my y-axis. Well, maybe you have this situation. You've got one line that goes across, and then you've got the other line that's exactly parallel. That can happen sometimes. And if that's the case, if these two lines are parallel, and I'll just draw these little parallel arrows to indicate that the lines are parallel just to make sure it's clear. But if that happens, if those two lines are parallel, they're never going to intersect, which means that this linear system has no solution. So the lines, I'll just write it down here, no solution. And the reason for that is that the two lines don't intersect, because if they're parallel and distinct lines, they'll never intersect. And there is actually a third possibility. That isn't accounted for in either of those first two cases. So there is a case 3. So what is case 3? Well, I'm going to draw a line like this. And it's possible that both of these two equations in this system are actually just different ways of describing the exact same line. So you might actually have the second line just drawn right over top. In which case, if you drew them over top of each other, you might just have a really thick line that tries to exaggerate the fact that both of these equations represent the same line. Now, well, what would happen if you have this situation? Well, that means if case 3 holds and both of these equations give you the same line, that would mean every single point on this line along which I'm tracing the pen's tip, all of these points are actually solutions to this linear system. And if that's the case, then that means it has infinitely many solutions, right? Every single point on this line is a point of intersection between the two lines, and hence it would be a solution to the system. So in this case, you have infinitely many solutions. Okay, so that is the key idea here. There's just those 3 possibilities. And it's actually probably worth, as an exercise, what I'd like you to do is just, even if you only spend 2 minutes after you pause this, after the end of this clip, just spend 2 minutes try to come up with another case where you draw 2 lines in R2, draw 2 straight lines that does not fall into one of these 3 cases. And really, you won't have to try long and you'll be convinced that it can't be done. Every possible way you could draw 2 different lines is going to look like one of these situations. Because think about it this way, the lines are either parallel or they aren't. If the lines aren't parallel, they're going to intersect. If the lines are parallel, well, they're either going to be different lines or they're going to be the same line. And so that leaves you with these 2 cases. If you would try to imagine how the lines could intersect exactly twice, well, you'd have to have one of the lines wrapping around and bending backwards, and that doesn't happen with straight lines. So I hope you're convinced that these are the only 3 things that can happen. But what's the point of that? 2 other things I want to mention right after, before we close this idea. So 2 facts. So 1, we've already said this, but I'll just write it down for emphasis. There are no other possibilities. And like I said, I encourage you to try to convince yourself of this by just trying to see if you can prove me wrong. Try to write down 2 lines that don't look like one of these 3 pictures. So that's the first fact. And the second fact, which is really the nice application of this, is that this generalizes, all of this discussion took place within the context of looking at a system of 2 equations in 2 variables. But in fact, my claim to you is that this phenomenon extends to any linear system of equations. Any number of equations and any number of variables. There's only going to be these 3 possibilities. 1 solution, no solution, or infinitely many solutions. So this generalizes to any linear system.